Isn't that true in all situations? The disadvantage have to rally together. Anyway, so if you wrote HBr in solution, you would write it as H plus and Br minus. Okay, right? But if you wrote acetic acid in water, you would keep it as just acetic acid, non-dissociated. Okay. So now let's take that and work with this. So for example, write molecular, total, and net ionic reactions for the following acid-base reactions. So for the Me equation, what does Me stand for? It stands for molecular equation. The TIE stands for total ionic equation. The NIE stands for net ionic reaction, or net ionic equation. Okay, so we have HI reacting with ammonia. And we have the TIE. Okay, so strategically, what I suggest is you go ahead and write out the reactants for the total ionic equation first. So without worrying about the Me equation, okay, let's go ahead and just write out the total ionic equation for this. So HI, what kind of compound is that? Acid or base? Acid. And what kind of acid is it?
Strong acid.
Strong acid. So in solution, how would we write this?
H plus aqueous plus
Right.
I.
Exactly. So it's going to be H plus. Now I'm just going to assume everything's aqueous just to save some time here. If it's not aqueous, then I'll change the phase. So HI in solution becomes H plus and I minus, because it's a strong acid. It fully dissociates. What about ammonia? How would I write that in solution? Right, it's going to stay together. It's going to stay as just NH3. And my products are going to be what?
Ammonium.
It's going to be ammonium and I minus. Okay, so once I have this, I could balance it. It's already balanced, it turns out. Okay. What about my products here on the molecular equation now?
Same thing.
Yeah, it'll be the same thing. Well, actually, yeah, it'll be the same. Well, for the molecular equation, okay, the reason why they call it molecular equation is because even strong electrolyte solutions or strong electrolytes, they are written still together in the molecular equation. So you can actually write it like this. It'd be NH4I. You know, the aqueous to tell the reader it breaks apart. It looks kind of weird, but that's how you write the molecular equation. All right, the total ionic equation shows that yes, this does indeed break up. Okay, what about the net equation? So what you do is, to get the net, you look at your total ionic equation and you ask yourself, are there any species that are the same on both sides of the arrow? And you'll see that iodide is the same. So if we cross those out and then keep the rest, okay, we'll have our net. So net-wise, we've got H plus reacted with ammonia to give us ammonia. Again, all phases aqueous. Okay. So to get from the total ionic to the net, you just have to cross out whatever's the same on both sides. All right. If something undergoes a change, then you can't take that out. So in this case, the iodide ion is the spectator ion. Am I making any sense? Hopefully. Mm-hmm. Okay. All right. What about the second one? Try that one on your own for a minute. See what you can do with that. Is anybody stuck? It's okay to admit it. This is hard. To me, this is difficult. So the first thing we did up here was we did our total ionic equation first. And then we worried about the molecular net after. What kind of compound is this? Strong acid. So how do we write it in the total ionic equation? Right. H plus or minus. What kind of compound is this? Weak base, right? So how do we write it? It stays together, right? If it's weak, it stays together. Okay. So what happens? What product do I get?
NH3.
Right, so this is NH2. Okay, if it gains an H plus, it becomes an NH3, right? So I'm going to do that. And then what's left is the perchlorate. Okay, is there something missing from that? The charge. What is the charge?
Plus.
It's still a plus. There you go. So analogous to the first example, H plus went to ammonia to give you NH4 plus. This is analogous to that. H plus goes to the NH2 and it becomes NH3. So it's the same thing as what the first one was, but it just looks different. But it's the pattern that I want you to see. You had a question, Jim?
Is it incorrect to put the hydrogen?
Usually what they do is they add the hydrogen to the existing hydrogen count.
Okay.
And the reason why is because it's the nitrogen that gains that extra hydrogen ion.
Okay.
And so you'll always see that. So this is now what we call an ammonium salt, or in this case a benzyl ammonium salt. Okay, ammonium salts are used with lots and lots of different amine-based drugs. Okay, and you'll see this pattern all the time. David, you had a question?
Yeah, I was a little confused on how the weak base is a positive charge.
So, okay, good point. Okay, so this is a weak base. Let's put a little more color coding here. So this is now We know this is a weak base, right? When it gains a hydrogen ion, is it still a base? And is it still a base or no? It's actually a weak acid now. Okay? So this is what we call the conjugate acid of the weak base. You may have heard those terms from Chem 107 too. Okay, and then this is, this was the acid, strong acid, and you could say this is now the conjugate base of that. So, very good question. Brought me to a point I wanted to make before. Yeah, all the.
I just had a question on, so it now has ammonia, so wouldn't it be a base or something?
So ammonia is a weak base. Ammonium is actually a weak acid. but because this is a weak acid on this side, but because this is a strong acid on this side, because this is strong on this side, it pushes the reaction to the right. Another way of saying it is hydroiodic acid wants to acidify the base a lot more than going backwards. Excuse me. So
It's just that the conjugated acid, that's the one that I'm a little confused on. Since NH3 is a weak base.
yeah, so the you're talking about this right here?
Yeah.
Okay, so are you okay with this being a weak base? Just okay. When it gains an H plus put onto it now has an extra proton. And when things have extra protons, they tend to be more acidic, not basic. So this is why we call it the conjugate acid, the Ca. Okay. So whatever has the extra hydrogen, is the acid, and whatever doesn't have the extra hydrogen is basic. Okay. So how do we complete this top reaction here? So just like this, we just combine it into a molecule now. So it's a C6H5 NH3 Cl4 aqueous. And again, the charges go away because we're not combining this. This is actually a soluble salt. Okay, you take a compound that's like ammonium iodide. If I asked you if that's soluble or insoluble, you tell me, well, it's an ammonium salt. All ammonium salts are soluble. Well, it's the same thing with this. This is an ammonium salt, but it just has a different group of atoms on it other than another hydrogen. And just like this, all perchlorates are soluble too, right? So same kind of idea. It looks strange, it looks weird, but it follows the pattern. Okay. So ideally, hopefully you're seeing a pattern built in with these. Do you see a pattern between this and this? Is the question, and that's what I want you to see. Net-wise, okay, what's the net reaction for this below? Are there any ions in the total ionic equation that are not changing? And the answer is yes. That would be perchlorate, right? Not chloride. Did I hear perchloride? Okay, perchlorate. So right, so perchlorate is the same on both sides. So I get rid of that. Those are my spectators. Excuse me. So net-wise, I have H plus, C6, H5, NH2. Going to C6, H5, NH3 plus. All right. Next one just has excuse me. Next one has a weak acid and a strong base. Okay, so how do we do that one? Maybe I can cram it here. We'll see. So try number 3. I'll give you a minute to see how far you go. Then we'll. All right, so how do we write this in solution? CH3COOH, same as what it is, right? Weak acid stays together. So we'll go ahead and write that. CH3COOH. How do we write sodium hydroxide in solution? Right, Na plus OH minus. Okay, what are my products?
H2O
Right, H2O.
plus Na plus CH3CO.
Right, CH3. Oh no, I'm running out of room. Uh-oh, minus. Okay. And then to complete this, it would just be H2O plus, and then combining the sodium and the acetate. You can write CO2 if you want, instead of CO. Again, what happened to the charges? This was plus, this was minus. What happened to the charges here? They disappear when you combine the ions together, right? So it's just like when you combine ions in nomenclature, right?
Where does the H2O come?
Good question. So the OH, so this hydroxide, needs a, so the H2O comes from the fact that this hydroxide, this OH negative, steals away this lone H plus dangling there by the acetic acid. And when it comes over, when this guy comes over to the hydroxide, it comes over as an H plus. Right? It's not just H by itself, it's H plus. So if you combine H plus with hydroxide, you get water. And again, what's left here? Only the protons moving over, the electrons are staying behind, and that's why this is negative charge on the acetate over here.
How do you know that you need to do that?
You know because, well, first of all, we recognized our players, right? We know that sodium hydroxide is a base, a strong base. We know that acetic acid is the acid. We're okay with identifying those, right? How do you know then that the H moves over here versus, say, like this H? Or versus, right. So with weak acids, with that OOH, that H at the end of the OO is always the acidic hydrogen. It's just understood that that's always the hydrogen that moves over. Okay, when we get to chapter 9, we'll get to Lewis structures, and you'll see a Lewis structure for acetic acid, and it's essentially a carbon double bonded to an oxygen and single bonded to the other oxygen, and the one with the single bonded oxygen has the hydrogen on it, and that one just comes off easily. So anytime you see OOH, whether it's on acetic acid or if I were to if I were to write, say, like C6H5COOH, right, here's another kind of weak acid. Right, again, what H comes off? It's always going to be the one at the end. So that's how you know which one comes off. Yeah, you got it.
Quick question to touch on that. So whenever there's a strong base involved, it's safe to say that it's going to produce a water, right?
Absolutely.
Okay.
Yeah, anytime you got hydroxide as a base, you'll always form water.
Okay.
It's only when you got the weak bases that you don't form water. You form some salt of the nitrogen compound.
And the strong acid.
Right. Okay, and then to finish this out, net-wise. So we look at the ions that are staying the same. Sodium is the same on both sides. So those are spectators. So net-wise, we get acetic acid with hydroxide. And we're going to form water and acetate. Notice, so when we balance chemical reactions, we always balance the atoms. But what a lot of people always forget about is you also have to obey the conservation of charge. So notice how the charge is the same collectively on both sides of the arrow. It's negative overall here, negative overall here. Right? So keeping track of the charge is very important for acid-base chemistry. Here it is typed out real nice if you want to look at that. All right, how are we doing? So with acid-base chemistry, it's identifying your players and just knowing how to write the chemistry based on that. You know. Let's see, a little bit of time left. All right. Last thing about acid-base chemistry. All of you have done a titration before if you've taken Chem 107. Okay. Acid-base titrations are probably the most common of all the titrations. We do have other kinds of titrations using redox or precipitation. What is a titration? It's a technique used to determine the concentration of a solution that you don't know by adding another solution that you do know the concentration of. Okay. From acid-base titrations, the stoichiometric point is reached, okay, when the moles of hydrogen ion are the same as the moles of hydroxide. Hence, you neutralize the solution. Okay, titrations are also done with precipitation of redox. So let's do an example problem of this. So, in the experiment, 50 milliliters of 0.15 molar nitric acid neutralized 30 mils of barium hydroxide. What is the concentration of the barium hydroxide solution? Okay. So what's the first thing we should do? Yeah, chemistry first, numbers later. Okay, so the chemistry, and I always suggest just using the molecular equation. It's just the easiest to do. So for the molecular equation, we have nitric acid, HNO3, and we got barium hydroxide. Now, it might not give you the formulas, and this probably gave you the formulas, but you might have to write the formulas to nomenclature, right? What are the products going to be? Right, so if you have hydroxide for a base, what are you going to form? Acidic hydrogen, here's your base. So you're going to get water from that. And then what's left? Barium nitrate. Formula for barium nitrate is what? BaNO3 parentheses 2. Again, all aqueous. Water is a liquid though. And then we got to balance this. How do we balance it? Right, you need 2 nitric acids, and that'll give you 2 waters. One quick way to do it is to say, well, okay, if I have 2 hydroxides and only 1 acid, okay, I need to have two acidic acids, 2 acidic hydrogens rather, to neutralize the solution. So this is our chemistry. Now we can do the numbers. So anyone remember how we did the last problem with molarity? So molarity is equal, moles are equal to volume times molarity. So again, this is molarity, moles, grams, but now it's just going to be molarity, moles, molarity. Okay. Okay, so what volume do we need here? We're given 50 and 30. Which volume do we use? Well, that 0.15 molar is specific to the nitric acid, which is, if you read it, is specific to the 50, right? All right, so doing that, we get 50 mLs. We need it in liters though, because molarity has units of liters. Right? So divide by 1,000 or multiply by 1,000? Divide by 1,000, right? So we have, or you could say 10 to the minus third liters for every 10 to the 0 mLs. Okay, going by our metric flipping out way of doing things. Okay, and then we have our molarity is 0.15 moles of HNO3 per 1 liter of solution. And then how do we get to moles of, well, what do we need to get to moles of? Yeah, what is the concentration of barium hydroxide? So instead of relating mole to mole ratio to a product, now we're concerned with barium hydroxide, which is another reactant. And the reason why is because the question is asking us, what's the concentration of this unknown barium hydroxide solution sitting in our flask that we're trying to figure out now? Okay, so it's for every 1 mole of barium hydroxide that we use up 2 moles of the nitric acid. All right, so that would give us 0.00375 moles of barium hydroxide. How do we get to molarity of barium hydroxide? We need to divide this by the liters of solution. What liters of solution do we divide by though? Do we divide by 50? Do we divide by 30? Do we divide by 80? So remember what the goal of the titration is. The goal of the titration is to figure out what is the molarity of the barium hydroxide in the original solution. Right? That's what we wanted. So what is the volume of the original solution? Before we added any nitric acid in there, what was the volume? It was 30, right? So always use, with the titration problem, original volume